Arif, let's just check if everybody's here.
Okay, everybody is okay. Yes.
Iberk, yes.
No, Ayberk is not here.
Not here.
I'm here.
Okay.
Okay, Ayberk. Yes, I see here.
Vitor Santos, yes. Joana.
Joanna.
Joana Henrique.
Yes, I'm here.
Okay.
Okay.
Maria Carrup. Maria.
Okay. Here.
No, not here.
Yes, she is. Yes, she is.
Oh,
Cristina.
sorry.
She's not with Cristina.
It's with the name Cristina. Okay. Sorry,
Okay.
Cristina. So, yes, sorry. I saw only Maria. Okay. And Mariana Santos, yes. Shatai, not yet.
Çağatay is another session now.
Okay, and he moves. Okay. Miguel Pereira.
Yes, I'm here.
Okay. And Sara Valdez. Yes.
Sara is here.
And Inês Cruz. No Inês, not here.
I'm here.
Oh, okay.
Okay.
So, and finally, Catarina Amaro. Okay.
I think Katerina is in my laboratory.
Yes.
And also sits my seat also.
Are from the lab, yes.
Thank you so much. First of all, I would like to thank Professor Rosaria and all of our participants to participate in our Congress IMASCON, and also say hi to everybody for my second country in Portugal. So I'm very pleasure to see here again, and also Professor Rosaria is an important person for me. So the microphone is your side, Professor.
Okay, thank you so much, Arif. I would like to thank Professor Arif for this opportunity. IMASCOM is now a reference in Turkey, and it's a pleasure and also a big challenge for us also to participate. So this is the IMASCOM Biomedical Talks. Not all the presentations will be directly connected to the biomedical domain, but normally I learn with my with Professor Rogério Leal that every domain is connected with other domain, even to get ideas. It will be important. So every of these presentations will be surely very interesting for all of us. So I think we can provide 8 minutes for each presentation, and maybe in the end we make a brainstorm of ideas, sharing ideas, putting questions, and so on. Everybody agree with this procedure? Yes?
Yes.
Yes.
Okay.
And also, Professor Rosario, with your permission, at the end of this session, I will share our university promotional video with your students.
Okay, good. Interesting. Okay, so maybe we make a change in the order. Sara Valdez will move to the one of the beginning, but let's start with Iberk Dizdar.
Okay. And also, Ayberk is my PhD student also in Biomedical Engineering Department. He's graduated at Biomedical Engineering Department in our university. So, Ayberk.
Okay, Arif, let me just say that we have in this meeting also Professor Ana Amaro from the university, and Professor, it's not Dimash, it's not...
I'm here. It's me, APP.
Okay. Okay.
Yes.
Thank you so much,
and
also for your support and to be in the meeting.
And also
No
Feyza
problem.
Nur, Erdem are our master
okay.
and doctoral students, PhD students in our university. They are in this session and they are the listener of this session.
Okay. So let's
Okay,
start.
Ayberk, let's start.
Okay, I shared my screen. Today, I present our studies titled Mechanical Performance of Rod Materials in Spinal Fusion. I collaborate with Salih Çelik and Arif Özkan. Spinal fusion is a surgical technique widely used to restore spinal stability. The procedure involves the permanent joining two more vertebrae and prevent the motion at the fused segment, thereby reducing mechanical stress and improving functionality. Role of rod materials. Rods are integral components of spinal fixation system, and their mechanical properties significantly impact. This study aims to evaluate the biomechanical performance of rod materials, titanium alloy, PEEK, and titanium alloy hybrids in spinal fusion procedures using the finite element analysis method. In this study, three parameters critical for bone remodeling were analyzed: compressive stress on the graft, microstrain at the screw bone interface, strain energy distribution at screw bone interface. Creating model, 3D spinal segment model including cortical, trabecular concylus, bone graft, pedicle screws, and rods was developed. Ligament model as a link element. We modeled as a tension only. We get the material properties from literature, and we also you get the information about contact definition from literature. Screw bone and graft bone interface assigned as a frictional contact, screw rod interface bonded. Boundary and loading conditions: 400 Newton vertical load and 80 nanometer moment applied to model. A tetrahedral mesh was used with higher density in screw bone and graft regions. Maximum stress values occurring on the rod according to analysis result. Higher rigidity of titanium alloy process significantly higher elastic modules compared to PEEK. Due to its increased stiffness, it undergoes less deformation under loading, resulting in higher stress concentration within material. PEEK is a lower elastic modulus, allowing it to distribute the applied load over a larger area. This leads to lower stress concentration compared to titanium load. Maximum strain energy also, first of all, we obtained compressive stress for graft. The variation of compressive stress on the graft is due to differing stiffness on the rod materials. Titanium rods with high rigidity transfer more load directly to the graft, increasing compressive stress, but unchanging stability. PEEK rods, being more flexible, absorb and distribute the load, reducing stress on the graft, but allowing written micromotion. Hybrid rods balance rigidity and flexibility, resulting in moderate compressive stress, providing both stability and better load distribution. Also, we obtained maximum strain energy and micro strain results. It's very important for bone remodeling. The table highlights mechanical response of the bone surrounding screws under different rod types. Titanium rods, due to their high stiffness, result low strain energy and microstrain to bone, which could lead to stress shielding and reduced bone remodeling stimulation. PEEK rods, with their greater flexibility, generate the high strain energy and microstrain, providing more physiological load distribution and potentially promoting bone remodeling. Discussion section. The findings of this study highlight the criteria role of raw material selection spin-off fusion biomechanics. Each material exhibits unique mechanical properties that influence the stability of the fusion construct, the distribution of stress, and micro-movements at the key interfaces ultimately affecting the clinical outcomes. Titanium rods rods provide the high rigidity, which ensures the excellent construct stability. The higher compressive stress on the graft may promote the early stabilization by reducing excessive motion. Disadvantage: the low strain energy at the screw bone interface limits the mechanical stimulation necessary for bone remodeling. This could potentially delay the fusion process and increase the risk of stress shielding. Peak advantage: peak rods offer high flexibility, allowing for better strain energy distribution at the screw bone interface. This characteristic is beneficial, promoting the bone growth and fusion at the contact sites. The increased micromovements observed with peak rods may compromise initial construct stability, particularly in patients with poor bone quality. Hybrid rods combine the rigidity of titanium alloy and the flexibility of PEEK, providing a balanced performance. They optimize stress distribution and stability, reducing risk of excessive micro movements while maintaining efficient mechanical stimulation for bone. Clinical implications: this material could be particularly advantageous in cases requiring a balance between stability and biological compatibility, such as osteoporotic or complex spinal fusion scenarios. Limitation of study: model simplification. The finite element model assumes idealized conditions, which may not fully replicate the complex in vivo environment. Loading conditions: static loads applied in the simulation represent the generalized conditions and do not account for patient-specific variability. Biological factors: this study focuses on mechanical outcomes, while biological factors such as cellular response and vascularization are not considered. Feature direction: incorporating patient-specific models based on CT or MRI data could enhance the applicability of the results. Long-term analysis: simulating progression of fusion over time, including effects of callus formation and bone remodeling, could provide deeper insights. Experimental validation: conducting mechanical tests on physical prototypes or cadaveric specimens could be validate the numerical findings. Thank you for listening.
Okay. Thank you so much. So we forward the base, the initial base, to put all the discussion together in the end, or do you think that make some discussion at this time? Arif,
Okay. And also,
Anna?
Ayberk has a good capability for finite element analysis and modeling of biomedical surfaces and other things, also biomedical materials. He is very good at on this session. So, is there any question for biomedical modeling or finite element analysis? Maybe he answered for all the questions.
Mhm.
Uh,
Okay.
Okay, thank you.
Thank you. So
Thank you.
now we have Vitor Santos. Vitor,
Okay, Victor. Thank you, Ayberk.
thank you, Ivek, and
You are welcome.
congratulations. We will discuss in the end, okay? Vitor, okay.
Can you see my presentation?
Yes,
Yes.
but
Yes.
in the yes presentation mode. Oh, yeah. Okay.
Yes.
Okay.
Now it's
Okay.
okay.
Good morning. First of all, I want to greet all members of the panel and thanks this opportunity to speak in this Congress. My name is Vitor Miguel Santos, and I am a researcher and a PhD student of mechanical engineering in the University of Coimbra. Today, I will present and talk briefly to you about wearable technology. So the title of my presentation is the following: the value of wearable technology and the path to optimization. Initially, it is important to understand what is wearable technology. Wearable technology is all type of equipment, devices that can be used in a non-invasive way, more like an accessory. It has the advantage to gather and share data to the user and others that is not easily seen to the eye. The structure of this presentation is the following. First, we are going to understand simply concepts of AI, machine learning, and data science, and what they can bring to the table. Second, we are going to present some applications that are impacted by these devices. Third, the obstacles to reach optimization of the equipment. And finally, some conclusions. With the technology evolution, it is expectable to appear more useful means to improve devices and make them valuable and precious to the users. So, with the rise of AI, it is natural to think the possibility of integrating this type of technology in wearables. To understand the concepts and dynamics, it is important to know what is AI, machine learning, and data science. AI, like the name tells us, is a technique that the main goal is to make computers imitate human behavior. Actions like discover information, read, and analyze from different sources and solve problems. Machine learning is part of AI and uses algorithms to extract data, analyze it, and even make decisions and predictions. They say more data equals more precision. Data science is present in AI and in machine learning, but it isn't AI. This field of knowledge has the mission to transform data in insights. So, the possibility of transforming raw data into insights is truly remarkable and can be a differential factor in the health, rehabilitation, and sports. In health and rehabilitation, these devices have the following advantages: monitor diseases and physical disorders for a long period of time, collect and analyze therapeutic activity data, for example, number of steps per day, the possibility to modify the planning routes and the type of procedures, and so concluding is beneficial to health professionals and patients with remote monitoring and early interventions. But how come? First, faster time to intervene and solve the problem. Second, possibility to gather extra information crucial to reach a better understanding. Third, more control and knowledge of the user's current state. Fourth, less urgency situations that need a supplementary human resources and healthcare system providers. Examples of wearable technology: Holter monitors, other wearable ECGs, and smart orthotics and insoles. Applications in sports. In sports, the focus is mainly in performance improvement, and the goal can be enhance some physical parameters or tactical positions, actions. With the use of this kind of equipment, it is possible to collect different metrics like acceleration, speed, distance, steps, heartbeat, and so on. In here, we present several types of equipment, and some of them are very used and already known to the public. For example, fitness trackers can obtain heart rate variability to predict recovery needs. GPS tracking is frequently used in football to collect players' position, covered area, real-time movements. After presenting some application of these devices, it is safe to say that there exists room to improve this kind of devices and apply them in other fields or in specific situations. So here, we present some of the challenges and opportunities that are expectable to rise in the development process. Cost. Devices must be affordable to all type of users. Design should be minimalistic to give a perception of a simple accessory and not a strange element. Comfort, allowing comfort to all users in daily life when doing all type of tasks and movements. Sensors. Number of sensors normally means more data, but influences directly in the energy consumption. ML can help solving this problem. The type of sensors and number depends on the application, and the placement of the sensor is also a challenge when manufacturing the prototype. Battery. Battery is a big problem that should be overcome with the technology evolution and with the integration of AI. Wireless connection is a plus by providing the user movement freedom, but has to be efficient in the transmission communication. Machine learning can help the users in providing valuable information in a faster way. Open source. To help the development of the products, it is important to have open source codes and database to facilitate the efficiency of the devices and offer valuable instrument to the public. Database. Number of data and database size is a problem because some information are closed and owned by entities and corporations, but it is important to protect the user's privacy. In conclusion, it is important to make this kind of technology affordable and accessible to the public. It is necessary to improve manufacturing process, design, and integrate latest technology. It is crucial to investigate more and learn the true value of these type of devices in several fields, areas, and specific tasks. Mandatory to show the potential of the technology and the ways they could improve people's lives. And finally, I would like to leave the following question. How far can we push the boundaries of technology to make lives better? Like I said previously, I work in the mechanical engineering department of the University of Coimbra, and me and my supervisors are currently investigating in this field. We already published one systematic review about insole sensor technology, and it is expectable to publish some more works about this or related themes. Thank you for your attention, and once more, I would like to thank to IMASCON for this opportunity.
Okay. Thank you so much for your presentation, Vitor. It's very interesting study also. Maybe next step, you will come here and we will do it together.
Okay.
Okay, Professor Rosario.
Thank you, Vitor. Thank you so much. We will be open for other questions. I don't know if you or your supervisors have more to say now. If not, we move forward. It's okay.
If there isn't any question.
Okay. Now we have questions, but in the end. Okay. Don't move, Vitor.
Okay. I don't.
Okay. Now we have Joana Henriques, and after Joana Henriques, we'll move Sara Valdez. Okay, because maybe she needs to to go out. So, Joanna, it's your turn. When you want, please.
Hocam geliyor bir saniye.
Can you see my presentation?
Yes, but in the full mode. Okay. Good
Okay,
now.
it's okay.
Yes. Yes.
So, good morning to all, and thank you for your presence today. My name is Joana Henriques, and I will present to you a small part of the work that I'm developing in SEMPR, which is related to the use of UV radiation as a disinfection tool and whether it is beneficial or detrimental. This is the outline of my presentation, and I will start to introduce the background that led to the research question. So, additive manufacturing, also known as 3D printing, has the capability to produce complex and custom-made parts with almost no waste. And for these reasons, it has been used in many applications, such as civil engineering, automotive, and aerospace, and even in the food industry. In the biomedical field, 3D printing has been explored to design personalized drug delivery systems, scaffolds, prosthetics, surgical devices, and also to produce models to train surgical procedures. Indeed, the use of 3D printing in biomedicine has shown improvements in healthcare sector because it is the basis of precision medicine. However, the implementation of such devices into clinical practice demands a crucial and intermediate step that consists of disinfecting any object that is going to be in contact with the human body. There are several ways to disinfect biomedical devices, and among these techniques, UV radiation can be pointed out as an effective and efficient strategy. UV radiation is responsible for damaging the RNA and DNA of biological organisms, preventing cellular replication. And when compared to other disinfection approaches, UV radiation is indicated as rapid and economical, with the ability to decontaminate at long distances with no physical contact being required. However, UV radiation can damage polymeric chains just like it harms the DNA, and eventually changing the properties of the material and compromising the mechanical behavior of the component. Bearing in mind these considerations, this work aims to answer some questions. Firstly, we wanted to know if the UV exposure affects the mechanical properties of two different materials manufactured through the FF technology. Then, we have explored the influence of some variables such as wavelength and exposure time in the mechanical properties of those materials. And finally, we have assessed the impact of storage conditions in the results. To do so, we designed the following workflow. Initially, we selected two different filaments that were chemically analyzed and thermically characterized to select optimal printing parameters. Then, the specimens were exposed to UV light for 30 or 60 minutes and stored in empty falcons or immersed in PBS solution for 1 week. And finally, the mechanical properties were evaluated with Sharpie test and hardness measurements, and FTIR spectroscopy was used to search for significant chemical modifications. Firstly, the filaments were chemically characterized to identify the functional groups of each polymer, and while the spectrum of EPs presents the characteristic bands of aromatic groups and butadiene, the spectrum of TPU shows the presence of urethane and ester bonds, which are characteristic of this polymer. Therefore, it can be assumed that the eventual presence of additives during the process of formation of these filaments did not induce significant changes in the chemical composition of the filaments. Then, the thermal stability of the filaments was studied and the results showed that both materials are stable for temperatures below 300 degrees. While IPS presents only one stage of degradation, TPU presents two stages of mass loss. Next, the SC was performed to study the thermal events of the polymeric materials. In the case of IPS, only one thermal event was identified, and on the other hand, TPU presents a melting temperature and two glass transition temperatures could be identified. After pre-characterizing the filaments, 3D printing step took place and the printing parameters used to produce the specimens are shown in the table. So we proceeded to the mechanical characterization of the materials, firstly by means of impact test. And the results show that overall, IPS presents higher values of impact strength and increased absorbed energy, which means that it is more prone to fracture. In turn, TPU did not suffer visible damage because of the elastomer-like behavior, which justifies the lower values. Although the wavelength and the exposure time did not introduce differences in the results, the way the samples were stored did. While the presence of water increased the impact strength of IPS, it has decreased this property in TPU. Then we measured the hardness of specimens. And since the materials have completely different behaviors, we had to use two different measuring methods. For IPS, we used Vickers microhardness, and the results did not present significant differences. For TPU, we used Shorhay hardness, and once again, the results are not different amongst the treatment conditions. Finally, we chemically characterized the specimens right after being exposed to UV light, and in the case of IPS, it can be seen that regardless of wavelength and exposure time, the characteristic chemical composition kept unchangeable, and this was also observed for TPU specimens, which means that UV did not promote chemical modifications on the polymeric materials. After analyzing the results, some conclusions may be presented. First, for the chemical characterization performed in this work, the UV exposure did not significantly affect the resulting properties. And secondly, neither the wavelength nor the exposure time had influence on those properties. Nonetheless, the storage condition introduced major differences in the final results. Therefore, and taking into consideration the title of this presentation, it can be concluded that UV disinfection is more prone to be beneficial than detrimental. And before ending my presentation, I would like to thank the FCT for the financial support, University of Coimbra, and SEMPRE. And I would like to acknowledge my supervisors as well. And with this, I end my presentation. Thank you for your attention.
Okay, thank you so much, Joanna, for your presentation. Very interesting.
Thank you.
Arif, do you want to say something?
No, thank you. Thanks for your presentation.
Thank you.
Okay. This in the end of session we'll discuss all together. And
Sure.
now we move to Sara Valdez.
Sarah,
Hello, Sara.
Yes.
Yes.
I'm
Okay.
trying to
share.
share the screen. Yeah. Okay. Can you see the screen?
Yes.
Okay.
Yes.
Yeah. Okay.
Please.
So,
Better.
hello, my name is Sara Valdez, and I will present. The title of my presentation is Material Selection for Left Atrial Appendage Models for Medical Training Simulators. So I'm a PhD student from University of Coimbra, and the motivation of this presentation is that stroke is a major public health problem, which is associated with high mortality rate. strokes are caused by blockage of blood to the brain and usually are caused by blood clots. These blood clots are formed during atrial fibrillation episodes and are usually formed in the left atrial appendage, which is a region of the heart with a distinctive internal and external morphology. When the blood enters in the left atrial appendage, so here, it is possible that the blood gets turned here in the reentrances and then increases its viscosity and then forms eventually a clot. So obviously there are several strategies for stroke prevention. However, the most widely used is a percutaneous strategy, which is a minimally invasive one, where occlusion devices are placed between the left atrial and the left atrial appendage in order to block the blood flow. So if the blood flow is blocked, the clot formation is not possible, or the releasing of those clots that may be already be formed. However, this strategy is efficient, but requires a perfect fit between the left atrial appendage and the occlusion device. Obviously, there are several commercial available occlusion devices in terms of size or in terms of type, but can the medical team be sure if the occlusion device is the right one for the case that the medical team have in hands? So, medical teams usually use cardiac simulators with customized physical models. It is well known that the closer the simulator is to the reality, the higher success rate of the outcomes. And therefore, the aim of this work is to find a material, a synthetic material, that can replicate the mechanical behavior of left atrial appendage biological tissue. But the question is how? So, the material and section methods. Okay, so in this research we use 5 materials. We selected 5 materials with different hardness values. Then we printed the samples with those materials, used fused filament fabrication technology. The samples were printed with grid infill pattern, and the second part of this research is to investigate the 2 printing parameters that have most influence in structural integrity of the specimens. So the number of shell, we use 1 or 2, and the infill density, we use 25 and 100%. And then the samples were characterized using tensile tests. So the results, the initial results were only used to select the 2 best materials for the problem that we have in hands. And the samples were tested were with 2 shell and 100% of infill. And according to the literature, the biological tissues of the myocardium have relatively low tensile stress maximum. So the most suitable materials, according to that range of values, are TPU 85A and TPE 60A. And then for the second part of the research, the printing parameters were evaluated. As it is possible to see, here we have a stress strain curve of the left atrial appendage that it is compared with the stress strain curve with of our printing samples. So it is possible to observe that the closest material in terms of maximum stress values is the TPE 60A with 1 shell and 25%. However, this is the best configuration that we can find, but the maximum values are still very high when compared with those with the left atrial appendage biological tissue, and the mechanical behavior does not fully mimic the mechanical behavior of the biological tissue. Also, during this research, it was also determined that lower infill values were not suitable, since it was not possible with that amount of material that the occlusion device can be anchored in this material if we can build a physical model. So as a future work, we intend to conduct a more in-depth study of the manufacturing parameters using this material, TPE 60A. So thank you. This was my presentation.
Okay, thank you so much.
Sorry. Okay.
Yes, want to share something more?
No. I stopped the record. Yeah.
Okay. Thank you so much, Sarah, for your
Thank you,
interesting
Professor.
work and presentation. Arif,
Thank you so much for Sarah for her
Thank you.
presentation. Also very interesting topic. Maybe you need the hard working so in near future.
okay. Thank you so
Yeah,
much,
thank you.
Sarah.
Thank you.
Let's hope that you can stay until the end.
Yeah.
And now we have Maria Carrupt. Maria.
Okay, let me share my presentation.
Okay.
Wait a minute, please. Ecrã inteiro. Can you see my presentation?
Yes, just put in the full mode. Yes.
Okay.
Okay, good.
So, good afternoon. First of all, I appreciate this invite to a presentation of my research, a part of my research. My name is Maria Cristina. I'm a PhD student, and I will a presentation of research about aging of thin films, silver and copper thin films. And these elements are important because have getting more and more attention from research because of their properties. And copper coatings are applied as antibacterial surface in biomedical area and have applications in more and more areas. So to understand how the effect of aging on these films, we develop monolithic and silver doped copper coatings were deposited using magnetosputter, PVD. Films with different contents of silver were prepared with the main objective to evaluate the impact of aging content on the wettability of Asian copper films. So the samples were divided in 3 different groups. The first one was kept as deposited. A part of samples was analyzed at 200 degrees, and the last one was left exposed in normal temperature and humidity condition during 1 year. And all of samples were characterized. The deposition was made in a PVD equipment. So parts of silver was placed on target of copper to cope deposition, and the deposition was made in a non-reactive atmosphere using argon. Sorry. The first results. The films were characterized about morphology using SAM, and we can see that the content of silver promotes an increase in the thickness of films. Due to the Latz parameter, according to Vanguard laws, when we have an increase in the contents of aging, it promotes an increase in the Latz parameter. So we can see here a little increase. With retreatment, promotes a severe increase in the thickness, and we see the film with more content of Ag, of silver. This growth is not so hard like this. This is because the diffusion of Ag of silver to grain boundary, and it difficulted the growth of thickness. Here, the content of silver, it was measured by the EDS. The films were characterized about structure, crystalline structure, and we can observe that in as the position condition, we can see the peaks of aging of silver. And after 1 year aging, the peaks of silver are not visible again. But after retreatment, this peak comes visible. Is it because, maybe because in this condition, because of the temperature of the position, the silver is in amorphous forms, or silver are coherent with copper matrix. With the temperature of retreatment, the silver comes to a crystalline form and the peaks are visible. We can see that the films have strong orientation according Plan 111. Is it because this specific equipment promotes this due to the cooling of substrate? So is in this condition, when the surface had lower surface energy, and with addition of silver, this we have an change. The conditions of planes change. We can see the plane 111 of silver and plane of copper. The retreatment promotes an oxidation of films, and we can see here, we can see a little peak of oxide here, but not in the other. But after retreatment, the peaks are clear. Here we can see with more detail the peaks of oxides. About wettability, the presence of silver promotes a little increase in surface energy, so in decrease in surface energy and more on a high angle contact angle. After 1 year of natural aging, the surface energy reduce, and we have an increase in the contact angle, as expected because of the oxidation of process of oxidation. The oxides are more stable. On the other hand, with retreatment, we have a decrease in contact angle and consequently an increase in surface energy. This can be because of the the growth of grain during the retreatment. Some authors attribute this effect to the grain growth. And we can infer too that the surface in this stage of after retreatment it's not in the most stable chemical configuration. So, some conclusions. The films are crystalline with FCC structure and crystallographic orientation according plan 111. However, with XRD analysis suggests that in next deposition film AG could be amorphous, and only after aniline does it become crystalline. The presence of silver promotes an increase in the thickness of films as deposition. During the aniline, silver restricts the increase of film thickness by restricting grain growth because of the diffusion of silver to grain boundary. The addition of silver also reduces the wettability of film in mass deposition condition and hydrate the degree of this texture development, namely after aniline, compared with copper film, because of the growth of the peaks 111 of silver. The aniline temperature promotes the formation of oxide, dioxide of copper and dioxide of silver, reduces the contact angles of films, and consequently improve the wettability. And it's all. Thank you for your attention.
Okay, thank you so much, Maria Cristina. Yes.
Sim.
Thank you so much for your presentation and your interesting work. Arif, want to say something?
Thank you so much.
Thank you.
And congratulations for the work also. Maybe we move forward to Mariana now, Mariana Santos.
Hi.
Okay, Mariana.
Okay, Mariana. Mm-hmm.
And also the view is so good for me because I miss my laboratory in ISAC.
Are you seeing something? Okay. So let's start. Good morning, everyone. I'd like to thank you for the opportunity to present my work today. My name is Mariana Santos. I'm a PhD student in mechanical engineering at the University of Coimbra. I'm here to present the topic from causes to prevention, addressing necrosis in total knee arthropathy, a work that it is in the beginning. So to guide this presentation, we will review the context behind the study and the research objectives. Then we will discuss the knee joint, the causes of the osteonecrosis, the advancements in total knee arthroplasty, and the point at which we are right now. The total knee arthroplasty is one of the most common procedures in orthopedics. Between 2010 and 2017, the numbers of the procedure increased significantly, highlighting the growth association with understanding complications such as necrosis. This context underlines the importance of exploring effective methods to prevent the issues. With this, we create a question that we are working with. The question is, what are the risk factors, prevention strategies, and numerical conclusions about femoral necrosis in patients undergoing total knee replacement? This study aims to identify the primary causes of post-arthroplasty necrosis and explore strategies to minimize associated risks. We strive to contribute to a better understanding and ultimately better patients' outcomes. The knee joint, starting from the beginning, it's a complex structure comprising the femur, cartilage, tibia, and artificial components, including metal and plastic parts in the case of prostheses. Any alterations or damage to this system can significantly impact joint functionality, leading to complications such as osteonecrosis. Osteonecrosis occurs when the blood supply to the bone is interrupted, resulting in cell death. In the context of knee arthroplasty, it can be caused by surgical manipulation, infections, or improper mechanical stress on the joint. This is called osteonecrosis spontaneous, but there are different reasons for it to appear. The total knee arthroplasty involves replacing surfaces with artificial components, including the metallical femoral components, in the plastic spacer. While this procedure effectively addressed pain and functional limitation, minimizing the risks of postoperative complication, otherwise the same procedure can cause harm because of the materials used to fix the prosthesis to the bone, such as cement. The temperature the cement needs to go for their work is dangerous to the bone. The limit of temperature to not appear necrosis in bone is 47 degrees, and the cement needs to reach almost 100 degrees. So we are in some way fixing a problem that can cause the same problem. Recent advancements include improvements in prosthesis materials and less invasive surgical techniques. However, ongoing research is essential to reduce complications like this one. Recent advancements include improvements in prosthesis material and less invasive surgical techniques. However, ongoing research is really necessary. Preventive strategies such as customized prostheses and strict postoperative monitoring have shown promising results. There is our subsequent work. We will do some numerical analysis and study the fixation methods to find connections that can provide an improvement in this fact, and that is our main goal. I would like to thank you for your time and attention. Thank you very much.
Okay, thanks for your presentation.
Thank you, Mariana. Arif, continue, please.
It's so important things. So biomedical components and redesign or new biomedical components are so important for our lives. So the designing process and then the mechanical properties of biomedical equipments are very important because of the quality of biomedical equipments going to less down. So these works are very valuable for us, for humanity also.
Okay.
Thank you.
Thank you. I think that Shatai is not yet here.
No, he's in another session now.
In another sessions.
Ended
So,
his session.
okay. So we have now Miguel Pereira. Miguel.
Yes, I'm here.
Miguel.
Okay.
So I'll share. So you can see the presentation, right?
Yes, put in the full mode, please. Yes.
It's not in full mode already?
No.
Okay, let me check. Mhm. Okay, so maybe now it's
Yes,
better.
now
Okay.
it's perfect. Okay.
Yes, for sure.
Okay, so my name is Miguel Pereira. I'm from the University of Coimbra, and I'm here to present part of my PhD, the optimization of metal polymer friction stir spot welding by texturing the metal surface.
Yes.
So the objective of my work is to produce an hybrid structure using the friction stir spot welding procedure, which can be improved by pre-treating the surface of the metal part. So today I will present what type of hybrid structures I'm using, how the friction stir spot welding procedure works, and which were the pretreatments that we studied. So there are many types of hybrid structures, but for us, we are considering hybrid structures composed of lightweight metal alloys, where we include aluminum and magnesium alloys, and the thermoplastic material. And for the thermoplastic material, we consider whether being reinforced or not with fibers. These materials are very important in a wide application, but here we consider that the ultimate goal is the transport sector, as the use of hybrid structures allow the production of lighter vehicles. And when we have lighter vehicles, we can reduce the fuel and energy consumption, which leads to economic savings and to the reduction of pollution. Regarding the friction stir welding process, it was developed in the Welding Institute by Wayne Thomas and his colleagues in 1991, and it uses a rotating tool, as shown in the right images, and this rotating tool softens the interfaces to be joined by means of heat generated by friction and severe plastic deformation. As illustrated, we can perform linear welding, which is the conventional friction stir welding, or spot welding, which is the process that we use, which is the friction stir spot welding. It is considered a simple process that normally does not require the use of a filler material or of a protected atmosphere, and is also considered safe and environmentally friendly, as there are no emissions of toxic fumes or UV radiations. In terms of welding conditions that we used the overlap joint configuration, and we used also always the aluminum with 1 millimeter of thickness positioned over the thermoplastic material. For the thermoplastic material, we consider two different materials, the first being non-reinforced polyamide 6, and the other glass fiber reinforced polyamide 6. The welding conditions that we tested several tool geometries where we observed that the pinless tools were those who revealed better results. But we tested also other welding conditions, welding parameters, which include rotational speed, plunge depth, and dwell time. Regarding the surface pretreatments that we tested, of course, we started by testing surface without pretreatment. Then we moved to a more simple process of just grinding. And then we tested two more unconventional processes for texturing the aluminum surface, which include circular texturing and mechanical groove. So first, as mentioned, we tested the production of joints without pretreating the aluminum, and we observed that these joints were easily separated by hand, which indicated the weakness of the joints produced in this condition. So we tested another approach, which was grinding the aluminum surface with sandpaper, and this resulted in an improvement of mechanical performance. The improvement of mechanical performance was attributed to the creation of a micro-interlocking mechanism, which is basically when we have the cooling or the solidification of the material, the polymeric material, in the rugosities created by the grinding procedure. But then we tested the circular texturing procedure, which is the process that leads to the more pleasant to the view results. And in this case, the circular texturing also improved the mechanical performance compared to the previous two. The improvement of mechanical performance is attributed to the creation of the mesomechanical interlocking mechanism, which in this case is due to the solidification of material in a larger portion of the texture. However, this procedure has a difficulty since tools typically break during the texturing procedure, as illustrated in this image. Finally, we tested the mechanical grooving procedure, which uses a tungsten carbide engraving tip to perform the treatment. It results in the shown multilinear pattern. And when we analyze the cross-section, which is here indicated on the right image, we see a serrated profile, which is composed of anchorage structures, as we can call teeth. So these anchorage structures warranty a better mesomechanical interlocking mechanism than the previous procedure. This type of mechanical grooving surface pretreatment resulted in the best surface pretreatment and in the best mechanical performance. So the conclusion is that using the friction stir spot welding and the mechanical grooving texturing pretreatment, the mechanical performance was greatly improved, and that the optimization of the texturing procedure and the welding parameters resulted in the case of aluminum polymer samples in polymer failure, and then as illustrated in this video, in the aluminum composite samples in aluminum failure. So we consider that these results demonstrate the success of our study. So thank you for your time, and thanks IMASCON for the invite.
Okay, thank you so much, Miguel, for your presentation and interesting work. No, Arif? No.
Thank you so much.
Okay. Okay, thank you, Miguel. Please stay to the questions in the end. And now we have Catarina Amaro. Hello, Catarina.
Estão a ver alguma coisa? Não, tu não precisas partilhar nada. Queres que eu alguma coisa? Tenho de ter partilhar, não é? Qual é que eu ponho? É esta?
Okay, good.
Estão a ver bem?
Let's start. Yes.
Good morning, everyone. My name is Catarina, and today I will present this study, which is part of my PhD research in sports biomechanics at the University of Coimbra. I would like to thank you for the opportunity to present my work here, and I hope that the next time it can be in person. Basketball shooting is a highly complex skill influenced by both technical and cognitive factors. In this study, we focus on the role of visual behavior, particularly the way athletes perceive visual information under different conditions. Our goal was to investigate how environmental constraints, such as opposition and gym audience noise, and shooting positions affect visual behavior and shooting accuracy. To illustrate the core concept of this study, I would like to show a short video. It highlights the distinction between looking and seeing. Vamos ver. So probably just in the second time that you watched the video was the time that you saw the moonwalking bear. And this distinction is particularly important in basketball, where quick and accurate visual proceeding can make the difference between scoring and missing a shot. Our methodology involved 18 athletes, 10 females and 8 male ones, performing shots from 3 positions, 45 degrees left, right, and in the middle, 90 degrees. All of them at a distance of 6.75 meters, which is the 3 points line. These shots were performed under 3 different conditions. The first one without constraints, the second one with a simulated opposition, and the third one with a simulated gym audience noise. For the equipment, we used the Tobii Pro Glasses 3, which is an equipment that measures visual behavior, specifically tracking, for example, fixation, saccades, time of quiet eye, and others. Calibration was performed before each acquisition, which means between each 10 shots, to ensure accurate data collection and consist in looking to a target for 2 or 3 seconds. Each athlete completed 10 shots in each condition and position, totaling 90 shots for each athlete. From this, we analyzed just the number and the total time of fixation. Also, we used the scoring system to evaluate shooting performance, ranging from 0, which is a missed shot without the ball touching the board or the rim or whatever, and the 4 is a scored shot with like a perfect shot. The ball doesn't touch the board, just rim. Here is a small video for an athlete during the exhibitions. I think the quality is not the best, but yeah, you can see the glasses and the boards. For data processing, we involved defining a fixation as any gaze held for at least 100 milliseconds within the area of interest. In our case, the area of interest was the rim and the boards near the rim, not all the boards, just like the small box. Statistically, analyses were conducted using SPSS, with the Wilcoxon test to determine significance. Our level of significance was set as 0.05. Moving to the results, we found that the number and total duration of fixation were significantly influenced by the experimental conditions. Specifically, the opposition condition led to fewer and shorter fixation. The simulated gym audience noise also reduced the duration of fixation. These differences were statistically significant, impacting how environmental constraints affect athletes' ability to focus visually. In terms of efficiency, shooting accuracy was highest in the no constraints condition across all positions. The presence of opposition and simulated audience noise reduced efficiency significantly. These results highlight the importance of minimizing distractions during practice to maximize performance in competitive settings. In conclusions, environmental constraints significantly influence visual behavior and shooting accuracy. Athletes performed better in conditions without opposition, both in terms of fixation behavior and efficiency. These findings suggest that visual training and simulation of high-pressure scenarios can enhance performance in basketball. I would like to thank my supervisors for their guidance, and lastly, I'm grateful to my team and participants for their contributions, and thank you all for your attention.
Okay, thank you so much for your presentation, Katarina. As a former basketball player, so it's so important and so nice topic for the PhD. But you need to hardworking and other things. So mechanical properties and mechanical are so problem for these topics. So you need the heart and you need the help, Professor Rosario. Can you hear me?
Yes, yes.
Okay.
Thank you so much. Of course, you are an expert in basketball, Arif, so very interesting the work of Katarina. Congratulations, Katarina. And okay, now we have the last presentation by Inês Cruz.
Consegue ver?
Yes.
Can you see?
Yes, okay,
Yes.
continue, please.
Okay. Good morning, everyone. I would like to thank you for the opportunity to present my work today. My name is Maria
And
Cruz.
also notice that 3 hours differences between our countries. So here is 4:30 p.m. now. So
good morning.
Yeah. Good afternoon.
It's true, okay.
Okay.
No, this is the job.
Okay. No problem. Okay, Inês, go.
I'm PhD student in mechanical engineering at the University of Coimbra. Today I'm going to present the results of my study, protective materials for strain gauge impacts on water sports biomechanics and potential industrial application. In sports such as rowing and canoeing, the combination of efficient technique and power generation is essential. Supported by precise biomechanical measurement, we are fundamental for analyzing and optimizing athletes' performance. Biomechanical devices such as strain gauge and measuring force and movements make it possible to instrument sports equipment and provide useful data for coach, athletes, and research. Wherever strain gauge face limitations like environmental factors such as temperature, humidity, vibrations, which can introduce some noise into the measurements, and some strategies such as thermal insulation, calibrations, sign-off filters, and protective materials such epoxy and silicone are used to mitigate these effects and increase the sensor resistance. For that, we try to investigate influence of 2 protective materials, ABM and PECOL, one behavior of strain gauge in dry and submerged conditions. ABM is a material recommended by the sensor manufacturer, and PECOL is a sealant usually used for boat repairs and not specifically developed to protect this type of sensors. Okay. Some factors we need to have in consideration because we will try to simulate the training conditions for canoeing and rowing. And for that, we try to have the sample material like the material we have in oar and the paddle, okay, carbon fiber. We use one directional strain gauge. We use a freestanding beam. It's like the sport we have in rowing and canoeing. Try to replace the same force with that athlete made in the paddle and the horse, and the protective materials that I talked before. But first, we made some tensile tests, try to characterize the material of the samples. In this table, we see the test conditions, and then we have the mechanical properties that we have in the results of our tests. We use a bidirectional strain gauge, try to have the mechanical properties in the direction of the fibers. The setup of our tests are developed by us. We try to use a motor. You can see here, I guess. This is a motor. We have a rotation screw to apply control displacement. And we use this guide liner to reduce friction. The motor is connected to Arduino Uno, and the strain gauge, what you see here in yellow, it's connected at the data acquisition model of National Instruments. Here you can see the setup in real life, and here is how to make the tests. This video. In this video, we'll see that we have displacement for up and down. And for the tests, we put display the speed rotation of the motor is 5 RPM. We have approximately 35 cycles, the loading and unloading. After its tests, we invert the samples and we try to make a pause of 10 minutes between tests to eliminate residual stress and establish baseline conditions for next steps. Here we have the samples. We have a control sample with a 2 strain gauge in both sides, one ABM sample and one Becquerel sample. The ABM and Becquerel sample are used in dry and submerged conditions. The control sample is only in dry conditions. For data collection, we made an interface in LabVIEW. This interface have a graph that just shows us the deformation, and we can control the time of the tests. And for data analysis, we made some routines. In this case, you can see here it's a routine for SPM. We use this analysis to understand the behavior of the curve of the strain gauge in the tests. I can show you next. Yes, here in the results you can see in dry connections, it's a comparison between the control and ABM. Here we can see in the gray area show you the difference between the control and ABM in all the curve made in the cycles. And for Becquerel, we see that you don't have the gray area. We don't have difference between the both. In case of submerged conditions, we see that ABM have a more established behavior, and control have now a gray area that have some difference between the Becquerel and control. Conclusions. ABM is more suitable for dry environments, have a high sensitivity, and the Becquerel show great stability but lower sensitivity. Maybe ABM it's more indicate for not submerged conditions and some dynamic scenarios because it's unpredictable. And the Becquerel is more versatile option and have more reliable in submerged environments. This study is focused in rowing and canoeing, but this study can be applied in different areas like structural monitoring in civil engineering and industrial process. This study can be used in different areas and can be applied at different sensors, not only strain gauge, but all other sensors. This is the team, me and my supervisors. And I want to thank you for the opportunity, and thanks to the FCT for the funding and all the collaboration of different universities that I have and the centers of investigation. Thank you for your attention.
Okay.
Thank you,
Thank you
Inês.
so much, Inês.
It's nice topic. When I was in Coimbra, we used wireless communication to get data on canoeing. So maybe Professor Rosario remains it. And also Professor Rosario and Vitor gets the data on the canoeing sports. It's so nice and interesting topic.
Thank you.
Yes, yes. Thank you, Ines. Can you stop sharing? Yes.
With your permission, I will share our university presentation film, only short, only 5 minutes to get for me. Is it possible, Professor Rosario?
Yes, yes, please.
Okay. Okay, pardon me. Can you hear the sound?
Yes,
Okay,
yes, sound
I
is
will
okay.
share it. This is my university, University of Kocaeli.
This is Kocaeli University, the shining education brand of Kocaeli, Turkey's industrial capital. Established in 1992, our university quickly became one of Turkey's large and strong universities and is working for our future both in education and science. With 840 education programs in associate, undergraduate, and graduate degrees in the fields of health, science, engineering, and social sciences, our university shed light on the future of more than 60,000 students. We are aware of our responsibility. With our expert academic and support staff, we stand by our students to ensure they receive the best education. We act with a proactive approach that aligns with the requirements of the era, regularly updating our strong infrastructure on which our educational services are based. Primarily in Umuttepe, which is one of the most prominent campuses in Turkey, we provide comfortable classrooms and study environments for our students in all educational areas of our university. With our advanced library services, we pave the way for our students and researchers to access information. We offer our students the privilege of being a member of Kocaeli University with advanced laboratory and application facilities where they can test their theoretical knowledge with practice. Aware of the importance of internationalization in contemporary university education, our university is strengthening opportunities for international education and research day by day, with the aim of becoming a global brand in education. Through bilateral agreements, especially Erasmus, we provide opportunities for both our researchers and students to gain international experience. We develop international quality standards, accreditation, and collaborations with the awareness that university education should be modern and universally recognized. Thus, we become a preferred university for foreign students seeking education in Turkey. In addition to educating the qualified workforce our country needs, we produce science for our country through research, R&D activities, and collaborations. With our research centers and technopark, we carry out projects and develop technologies in areas needed for the development of our country. As the brand value of an industrial city, we offer the science we produce to the service of the industry. Through our bilateral agreements, we support production and stand alongside Turkey's leading brands. We both carry out R&D studies demanded by our industry and provide internship opportunities for our students to enhance their experiences. With the honor of carrying the name of our city, we develop projects that align with the needs of our city and region and stand by our people with all our facilities. With our research and application hospital, which has one of the most modern infrastructures in Turkey, we make a difference in healthcare services and provide quality healthcare not only for the local community, but also for our country. We care about the happiness of our students. In Kocaeli, which stands out with its tourism opportunities and city life, besides being known as an industrial city, we provide our students with the social facilities they desire and need. With the approach that a happy student is a successful student, we act with the awareness that academic success will not be limited only to the quality of education. With more than 100 student clubs, indoor and outdoor sports facilities, swimming pool, social living areas, dining halls, health services, sports and cultural activities, we're always working to make our students feel that we're always there for them. The 21st century is the age of technology, science, and change. We are aware of our responsibility. We work for the success of our students and for the future of science. Altogether, we educate, research, and produce.
Okay, thank you, Arif, for sharing.
Thank you so much.
I can say that all of that is very beautiful, and it remains one thing in the film, Arif. All the people are very, 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 very friendly and very good people. We love your country. Thank you so much for sharing your university. I think that if some of the students and colleagues here have questions, can put directly to you questions about the possibilities for mobility, possibilities for research and other things. Maybe they can contact directly to you.
Yes.
Okay.
Every time, whatever you want. Only directly contact me with email or my WhatsApp number or GSM number. That's enough. Do not hesitate to contact me. And also, if you need to get exchange program, and we are very happy to come here and educate our master or PhD degree. We are very happy.
Okay, thank you. Now let's make some discussion about the presentations, about the works. We have several works, very interesting works in the different domains, but we can say that all of them can be connected, interconnected. I don't know if someone from the people, from the colleagues that are in the panel, in the meeting, wanted to ask something first.
Çocuklar, bizden sormak istediğiniz bir şey var mı? With your permission, I am continuing in Turkish for my students.
Okay.
Feyza Nur Erdem, sormak
Çok
istediğiniz bir
teşekkür
şey var
ederiz
mı?
hocam. Çok sağ olun. Şu anlık bir sorumuz yok. Güzel bir seminerdi.
Okay.
Okay. And
Yes.
Paul, you want to put some questions, your impressions?
Thank you, Luis, and thank you for allowing me to assist to this gathering, let's say, and presentations of the students from Turkish and Coimbra University. And I think it was very interesting because we have several views that all come together for the biomedical, biomechanical, and those activities. And in fact, it's something that we need because we need to have not only multidisciplinarity, but we need to have interdisciplinarity. So we need the students to begin to solve problems which are every time more transversal to several areas of knowledge. So I think gatherings like this make an excellent opportunity for students and us ourselves learn some things. I'm not going to make any questions because the students, if they want to make between them, I think it's okay, but not for me. I'm not very happy to do them. Okay.
And also, finally,
you.
my base is on biomedical engineering studies, but I'm a mechanical engineer. But we are the capability of electronic side and other bio application side. So we are open all the works together with
Well,
you.
I'm in the Department of Mechanical Engineering, Coimbra, but I'm a biochemistry.
Yes, I'm a
My
mechanical
bachelor
engineering too.
is biochemistry, so
Thank you so much.
it goes around and comes around,
Yes.
right?
Okay. Anna, do you want to say something?
Hello, everybody. No,
Thank
I would like to thank for the opportunity for me or for my PhD students to present their studies. There are different kind of studies. For example, Miguel works in the really in the mechanical engineering, and Inês, Mariana, Joana, and Miguel in the biomechanical. So I think it is very interesting for them to assist and to present their works. So thanks you again.
Okay, thank you so much. I completely agree with what Paula said, uh, because more than particular questions about the work, about the mechanical things, about the biomedical things, of course, there will be a lot of questions that but this sharing, all of this possibility for sharing, also between several different PhD students, I think will get a big beneficial, and maybe also for all of them in the future. But of course, we are open if someone want to put particular questions for all the participants. No,
Thank you.
and not technical, but considering all of these, of that this possibility, someone that have been present here want to share some idea, want to share something.
For me or your side?
From no matter, from this panel, these
Okay.
talks. No.
Now I share my contact details via messaging options in this Teams works. So, and also approximately 2 weeks later, we will share the abstract book for you.
Okay,
Okay.
let's
Thank you.
explain to all
That's
that
the news of my site.
Arif, let's explain to all that all the written must be correctly in the template. Some
Okay.
of them are correct, but as I understood, others are not absolutely
At
correct.
this night, I will check and send you these are correct or not.
And also the certificates will be sent. Maybe you send it to me,
Yes.
and I will distribute, or as
I
you
will
want.
Okay. I think that tomorrow I will send all certificates for you with your
Okay.
mail, maybe, and also send on via internet or WhatsApp.
Okay, for all the participants, we hope, me and Arif, that it was a great time here. We have almost 2 hours because a lot of presentations. Sorry for being just 8 minutes. Sorry not to go forward with the questions and put all of this to a final discussion. But the time is going, and we wish that for each of you developing your PhD work, this have been also an interesting opportunity to share your work, to share your challenges, also to share. I saw very vibrant presentations that is very good, very interesting, and please continue.
Okay. Obrigado, meu amigo. My Portuguese is only small.
And for all the colleagues and students from Turkey, of course, say that we are also open to share our knowledge. Portugal is a very friendly country also, with
And
lovely
also
people also.
Portugal is my second hometown. So You're very similar for my people, with my people, sorry. So it's so calm for me.
And please, Arif, if it is necessary, translate in Turkish and say, I can say that to Çekular, to all of you.
Teşekkürler. Thank you, obrigado.
Thank you, obrigado.
It's so hard to check the sound. So yes, I know Turkish sounds and pronunciation is not so simple. That's the reason. Teşekkürler is equals to obrigado as your language.
Yeah, it's better a kebab, but we can try to talk.
De nada.
Goodbye.
Bye. Thank you.
Thank you so much.
Bye bye.
Bye.
Bye. Thank you.
Goodbye. Thank you. See you. Bye.